This is Review Lecture 5 for my review course of Undergraduate Probability and Statistics. I'm Chris Mack, and this is Probability Part 2, where we're going to talk about counting. Now, you might think you already know how to count, but when the number of items you need to count becomes quite large, maybe significantly larger than the number of fingers or toes that you have, counting can become difficult. But there are some techniques that allow us to count even very large numbers of things reasonably well. And that's what we're going to talk about in this lecture. But first, why are we talking about counting? We're talking about probability, aren't we? Well, there is something called the Discrete Uniform Probability Model, which is very common and very useful in some circumstances. Consider a deck of cards, and I ask you the question, what's the probability of drawing an ace of spades? Well, to answer that question, we probably already know the answer. If there's 52 cards and it's well shuffled so that I have a random probability of selecting any card, well, then I would say the probability of selecting the ace of spades is 1 out of 52, 1/52. Well, we can generalize this case to the case of a discrete finite sample space of size n. Then, if I can define the probability of every outcome, I can define the probability law for everything, right? But many real and important problems have random uniform probability laws. What I mean by that is I have an equal probability of selecting any particular outcome. In other words, the probability of selecting a particular outcome is simply 1 over n. We call this a uniform probability law. Every single item has the same probability. Every single outcome has the same probability of occurring. And since the probability of the sample space has to be 1, that means the probability of any given outcome must be 1 over m. We call this the classical probability concept, and the reason it's classical is probability developed on the order of 500 years ago, 400 years ago, in its earliest stages, to describe gambling. And games of chance tend to have uniform probability, unless you have loaded dice or a card shark. Generally, dealing cards or rolling a dice, there's a uniform probability of any event occurring. Now, if I look at an event E, some collection of outcomes, I can define the probability of that event in a very simple way for the case of a uniform probability law. I simply count the number of elements in E and then divide by the total number of elements in my sample space. Symbolically, we use this absolute value sign on E, or the absolute value sign on omega for the sample space, to describe the cardinality of the set. That simply means the number of elements in that set. In this way, for this case of a discrete uniform probability model, determining probabilities is simply a counting problem. I count the number of elements in E, divide by the total number of elements in the sample space, and I'm done. For example, what's the probability of drawing a heart from a well-shuffled deck of cards? Now, I say things like well-shuffled to imply that it is a random selection. How do I determine the probability of drawing a heart? I count the number of hearts in the deck and divide by the number of cards in the deck. There are 13 hearts in a deck of cards, 52 cards. Divide 13 by 52, I get 1/4. So 25% probability of that event. You see, counting helps us determine probabilities. So let's look at some counting. Another way of describing counting is combinatorial analysis. Sometimes counting can be hard. How many phone numbers are there in the 512 area code? How many different poker hands are there? How many different license plates can you make in the state of Texas? These are examples of counting problems, and often the answers to these problems are very important to know. We have some general rules that we can apply to counting problems, and the first rule is to count by partitioning. We partition into cases, and then we look at the number in each case. So, the sum rule. Suppose I have two disjoint sets, A and B, and I want to pick one element from A or one element from B. How many different choices are there? How many different ways are there to get these to get a particular pick? Well, I have to add the number of elements in A to the number of elements in B if I'm picking A or B. What if I'm going to pick A and B? I have two sets, A and B. Now they don't have to be disjoint, but I pick one element from A and one element from B. How many choices are there? Well, it's the product of the cardinalities of the two sets. That is the product of the number of elements. I'll give you an example. We're going to go through a few examples here to make this a little clearer. Suppose you're going to choose between doing your homework tonight in one of your 3 classes or going to one of 4 movies that are at the local theater. If it's an or, then how many different options do I have? Well, I have a total of 7 options. I use the sum rule. But what if I'm going to do homework in one of my 3 classes and then I'm going to go to a movie and I have 4 movies to choose from? Well, now how many different options are there? Well, I use the product rule. 3 different options for which class I'm going to do the homework in, and 4 different options for which movie I'm going to go in. Now, I know that these would not be realistic choices for any of you listening here, because if you were taking 3 classes, I'm sure all of you would do the homework for all 3 classes every night. But in this case, another hypothetical person would have 12 options in this product rule example. Well, these are relatively simple cases, but sometimes the number of options gets larger and larger and larger. The stage counting method is the fundamental method that we use to break a complicated problem down into a simpler problem. That is, we break the counting problem into some number R independent stages. Then, for stage 1, the first step, I count how many options there are. Suppose there's n1 options. Then I do stage 2. How many options are there in stage 2? Well, there's n2 options, etc. Because I'm going to do stage 1 and stage 2 and stage 3 and stage 4 all the way up to stage n, I will use the product rule to determine the total number of options. So I multiply n1 times n2 times n3 all the way up to nr, and that product becomes the total number of options available when I've broken my process down into these independent stages. In other words, at stage 1, let's say I have 3 choices. I can draw a branch diagram that shows branching off into these 3 options. Then at stage 2, I have, say, 2 options. So for each branch of stage 1, I have 2 options available. Now, here's the key. These are independent stages. In other words, my 2 choices that I have at stage 2 are independent of which choice I made at stage 1. If they're not independent, then it's a whole different counting problem. But if they are independent, the number of choices I have at stage 2 is independent of which choice I made at stage 1, then I always have 2 choices for each outcome from stage 1. And then let's suppose at stage 3 I have 3 choices available. Well, how do I figure out the total number of choices, total number of options available at the end? Well, I multiply the number in stage 1, which was 3, times the number of options in stage 2, which was 2, times the number of options in stage 3, which was 3, 3 times 2 times 3, that's 18. And if I count them up, sure enough, there are 18 branches at the end of the final stage. Let's look at some examples. I asked this question: how many phone numbers are in the 512 area code? In the United States, we have 7 digits in our phone number other than the area code. But there are some constraints. So let's look at this process and we'll break it up into stages. The first stage will be picking the first number. I'm going to pick the first number of my phone number. How many choices do I have? Well, in the United States, we cannot have a 0 or a 1 is the first digit of our phone number, so that leaves 8 other digits available. There are 8 options. N1 equals 8 for stage 1. Now we pick the second number. There are 10 options available for the second number. N1 equals 10. We continue this process on. The last stage, picking the last number, there are again 10 digits available to pick. When I multiply all the stage counts, I have a total of 8 times 10 times 10 times 10, etc. for 8 million phone numbers. That's how many phone numbers there are in a particular area code. In the city of Austin, where I live, we have the 512 area code. We recently ran out of phone numbers. There's not 8 million people living in the 512 area code, but people have so many phones, work phone, home phone, cell phone, fax, etc., that we have now run out of the 8 million phone numbers available, and we had to pick a second area code for the city of Austin. Here's another counting example. I'm going to make license plates, and my license plates will be 3 letters followed by 3 numbers. If that is the format of my license plate, how many are possible? Well, again, we pick the first letter of the license plate. There are 26 choices. We pick the second letter of the license plate, 26 choices. Third letter, 26 choices. Then 3 numbers. There are 10 choices, 10 choices, and 10 choices. I might multiply all that together. For license plates of the format 3 letters followed by 3 numbers, there are a little over 17 million license plates that are unique. Now note that in this counting example, order matters. A license plate ABC123 is not the same as a license plate CAB321. Order matters. If order didn't matter, I'd have to count differently, and we'll talk about that as well. When order matters, we have what is called a string. A string is, in particular, orderings of characters with repetitions allowed. That is, I'm allowed to have the same letter twice in my license plate. Orderings with repetition is called a string, and we can use the product rule to figure out how to count. Here's another example where ordering doesn't matter. If I have a set, and this set has n elements, how many different subsets are possible? Now in this case, a set, when I list the elements of a particular set, the order that I list them in doesn't matter. Sets don't care about the ordering of the elements. It's only what elements are in there. And a subset could have 1 element in it, or 2, or 5, or any number of elements. So how would I go about figuring out how many subsets are possible for a set with n elements? The key is to come up with a process of stages for creating the subset. And in this case, the simplest way is to simply ask for every element, is it in the subset, yes or no? So, stage 1, I'll look at the first element in the set and ask, is it in the subset? There's only 2 possibilities, yes or no. So the number of options, 2. I go to the second element in the set and ask, have I picked this one for the subset, yes or no? So again, there's only 2 options. I do that for every single element of the n elements of my set, and the total number of possible subsets is 2 to the n. Here's another example. How many different ways can you line up 5 people for a photograph? right? You're lining up people who are at a wedding, let's say. And I have 5 people that I need to put them in a particular order. Now, order matters in this particular case. Again, I pick a process for creating the ordered line of 5 people that is done in stages. And just think about how you would actually do this if you were the photographer and you got to pick. You got these 5 people and you say, all right, the first person in line, let me pick that first person. Well, how many options are there? I've got 5 people in the group. I pick them, put the first one in line, boom. 5 is the number of options for stage 1. At stage 2, I pick the second person in line, but now I don't have 5 people to choose from, I only have 4 people. This is picking without replacement or without repetition. Once a person is picked to go in the line, he can't be picked a second time to go somewhere else in the line. So there's only 4 options available in the second choice, the second stage. The third stage, I pick the third person in the line, and now there's only 3 people left in my group. On and on, multiply all the stage counts. 5 times 4 times 3 times 2 times 1. We have a name for this kind of multiplication of decreasing numbers. We call it factorial. So the total number of ways in which I can line up 5 people out of a group of 5 for a photograph is 5 factorial. We call this orderings without repetitions or replacements. We call this permutations. How many different ways can I permutate these 5 people? That is, order them up in a sequence. And the answer is, for n elements in a set, there's n factorial permutations, ways of sequencing them. Another interesting example is k-permutations. That is, I have a larger group, let's say 8, but I want to select only 3 of them and line them up. How many different ways can I sequence 3 people selected from a group of 8? Again, we can figure this out using the stage process. Stage 1, pick the first person in your line. How many options are available? Well, there's 8. 8 people in the group. I can pick any one of those 8. Now, pick the second person in line. I only have 7 people left in my group. The third person in line, I only have 6 people left in my group, so I have 6 options to choose from. I multiply them all together, 8 times 7 times 6. Now, another way of writing 8 times 7 times 6, you may not have thought of this as a way of writing down that, but I can describe it as 8 factorial divided by 5 factorial. Think about that. Maybe even write it out and see if you're convinced that that's true. So, if I have a set of n, and I want to select k, a subset of k, and order those people to create a sequence out of that set of n, how many different ways can I do it? Well, this is a common problem, so we have a little symbol we use. Out of n, permutate k of them. That's called the k-permutations out of n. And the answer is n factorial divided by n minus k factorial. But sometimes order doesn't matter. When order doesn't matter, we don't call it a permutation, we call it a combination. How many different subsets are possible when selecting k elements out of a set of n? Now remember, for a subset, the order doesn't matter. And I'm going to select exactly k elements for my subset out of a total of n. Now, how many different subsets are possible? This is called a combination. Order doesn't matter, but there is no replacement. Once I pick an element out, I don't put it back. It's not available to be picked again. So, let me define a symbol to represent the answer to this question. The number of combinations will have this kind of strange looking symbol. It's parentheses with n over a k. This is read as n choose k. So I have n, and I'm going to choose k elements out of that total of n. And what is the total number of ways I can do that? That's what this symbol represents. Now I don't know what the answer is. I just wrote a symbol to represent the answer, but I don't know what the answer is. Let's derive that. And I'll do it by using a two-step derivation based on the k-permutations results that we just got before. So, to create a combination, I'll do a two-stage derivation of the k-permutations result. In stage one, I'm going to pick a k subset. How many different k subsets are there out of a set of n? Well, we don't know the answer yet, but we have a symbol to represent that answer. It's n choose k. Now, the second step is I've got a k subset. How many different ways can I order them? Well, we do know the answer to that. The number of ways of ordering k elements is k factorial. So, to create the total number of k permutations, I'm going to start by picking first a k subset, then I'm going to order them. Now, the total number then will be the product of the two stages, n choose k multiplied by k factorial. Well, this is the number of k permutations. But I already know the number of k permutations. So we derived that earlier. So let me now derive the value for n choose k by simply taking the number of k permutations and dividing by k factorial. Number of k permutations was n factorial divided by n minus k factorial. I take that, divide by k factorial, and that gives me n choose k. So I've derived an answer for my question: how many different subsets of size k can I make out of a set of size n? Let's do another counting example. How many different 5-card poker hands are there? So a 5-card poker hand means I'm taking a deck of 52 cards and shuffling them so that they're randomized and then selecting 5 cards out of it. Well, it's drawing without replacement. Order doesn't matter. So that's n choose k, where n is 52 and k is 5. Calculate n choose k. That's 52 choose 5. I've got 52 factorial over 5 factorial and over 52 minus 5 factorial. In other words, that's 52 times 51 times 50 times 49 times 48. And then after that, 47 and beyond gets canceled out by what's on the bottom. And then I divide by 5 factorial, 5 times 4 times 3 times 2 times 1. And that whole thing is about 2.6 million. So that's how many 5-card poker hands there are. The key is to think about, am I drawing with or without replacement? Does order matter, yes or no? And that helps to answer this kind of counting problem. So let's look at all of the possibilities of combinatorics. I'm going to draw k from a set of n. I'm going to draw it either with and without replacement, and either order matters or it doesn't. If I'm drawing with replacement and order matters, well, then I have the simple product rule, n to the k. This is like how many phone numbers are there, or how many license plates, etc. Simple product rule applies, n times n times n. I do it k times. If order doesn't matter, well, then I simply take the total number of options when order doesn't matter. When order does matter here, and divide by the permutations, k factorial, and that tells me how many subsets k I can get from a set n if I'm drawing with replacement, but order doesn't matter. If I'm drawing without replacement, we have the options that we've just talked about, k permutations if order matters, n factorial divided by n minus k factorial, and if order doesn't matter, I have the combinations n choose k. Given these answers for these kinds of drawings, I now apply my stage process break any complicated problem into individual stages, where each stage can be thought of as one of the above types, and then I multiply all of these things together to get my answer. Of course, it requires that each stage is independent, but that works for many, many different problems. All right, what have we learned in lecture number 5 here? Our second lecture in a series of probabilities. As always, you should be able to quickly and easily answer these questions. If not, you need to go back and review the material a little bit more. Under what circumstances does a probability law turn into merely a counting problem? Define the sum rule and the product rule and when we can use those rules. What is the stage counting method? What is the difference between a permutation and a combination? And finally, what does drawing with replacement mean as compared to drawing without replacement? Well, that's the end of our second lecture on probability. Next time we'll have the third and final lecture on probability. Till then.